Hello everyone, it's Dr. Yazdani here. Today we're going to take a break from ECGs and talk about VBGs or ABGs for a change. Blood gas reports are extremely valuable in the workup of acutely unwell patients. Biochem labs usually take an hour or more. Until then, your blood gas can provide valuable insight into what's going on and give some direction to your treatment plan. Let's talk about the acid-base components of a blood gas today. I'm a big fan of memorizing normal values. I strongly recommend learning these numbers by heart. The pH is an indicator of the acid-base balance. The normal pH ranges from 7.35 to 7.45. Values below 7.35 suggest acidosis, and values higher than 7.45 indicate alkalosis. The two major players in the acid-base game are CO2 pressure and bicarbonate. These are the body's tools to maintain the acid-base balance. The normal range for an arterial PCO2 is 4.7 to 6. The normal range for bicarbonate is 22 to 28. Carbon dioxide is obviously a respiratory parameter. Bicarbonate, on the other hand, is a metabolic component managed by the kidneys. Higher CO2 pressures mean more acidity or less alkalosis. Lower CO2 means less acidosis or more alkalosis by extension. Higher bicarbonate levels make blood more alkaline or less acidic. Lower bicarbonate, in turn, makes it less alkaline or more acidic. Before moving on, here is a recap of what we've covered so far. Normal ABG values. pH 7.35 to 7.45. PCO2 4.7 to 6. Bicarbonate 22 to 28. Lower pH means acidosis. Higher pH means alkalosis. PCO2 is the respiratory component. Bicarbonate is the metabolic component. Higher PCO2 causes acidosis. Lower PCO2 causes alkalosis. Higher bicarbonate causes alkalosis. Lower bicarbonate results in acidosis. Now, you can easily tell if there is acidosis or alkalosis by simply looking at the pH. Then decide if the shift in the pH is respiratory or metabolic. Whichever component has shifted in the direction of the pH will give it its name, respiratory or metabolic. Let's assume your patient has an acidic pH of 7.2. Your PCO2 is 7 and bicarb is 22. Which of these has shifted in the direction of your pH? Yes, the respiratory component, or CO2. Therefore, this is a case of respiratory acidosis, as in COPD patients. The body will then try to restore the pH back to normal and compensate, in this case, by producing more bicarbonate, the metabolic component of your gas, to neutralize the acidity that has originated from the patient's respiratory condition. COPD patients who retain CO2, the so-called chronic retainers, often have elevated bicarbonate levels to maintain compensation. If the pH is low and the pathology is in the patient's breathing, your acidosis is more likely to be respiratory in nature. If the pH is low and so is your bicarbonate, the metabolic component, then your acidosis is metabolic. Diabetic patients, for instance, may become acidotic due to poor blood sugar control, a metabolic process that is associated with low bicarbonate. In other words, metabolic acidosis, seen in DKA. These patients are often seen breathing rapidly in order to compensate by venting off CO2 to make the blood less acidic. The drop in PCO2 seen in DKA patients is therefore respiratory compensation. By the same token, if the pH is high, alkalotic, and PCO2 is low, then your alkalosis is respiratory. Anxious, hyperventilating patients are a good example. Anxiety drives rapid breathing, so these patients drop their CO2 pressure and their blood becomes alkalotic or less acidic. The body then starts neutralizing this respiratory alkalosis by activating metabolic compensation, which of course means reducing bicarbonate levels. So, You may see a pH of 7.5 in an anxious patient with a PCO2 of 3.5 and a compensated bicarb of, say, 18. If the pH is high and your bicarbonate is high too, your alkalosis is metabolic, as in excessive vomiting or diuretic overuse. The body's expected response would be to change your breathing pattern to increase the acidity and try to neutralize the metabolic alkalosis by retaining CO2 through hypoventilation, which of course will also result in hypoxia and the complications associated with it. Anyways, before compensation, it won't be too difficult to identify the different types of acid-base abnormality. The task becomes more difficult when the body successfully does some compensation and normalizes the pH, and you set out to determine the original pathology and the type of compensation. At this point, we need some clinical context to identify the initial pathology and the type of body's response in order to compensate. In the upcoming episodes, we'll talk about other components of the blood gas and their significance. Until then, stay safe and thank you for watching.